Questions about Lab 3? So you had a long discussion last night, Darvin, I think about generate statements.
Yes.
Yeah, so what happened with that? What was there anything you found obscure about generate statements?
I wouldn't say it was obscure. I think the design was just, the way the design was coded up just really...
So it was hard to turn into a generate.
The design was using multi-dimensional arrays to index multi-dimensional arrays. So, yeah.
Okay. All right, so simplification of the design was more important than unscrambling the generate. Yeah. Okay. Okay. Any other questions about Lab 3?
Well, there was one weird thing was that when you disconnected the audio output to the state machine, then the bug that apparently was caused by the generate statement. So I'm assuming that was some kind of like optimization.
Yeah, I'm guessing that if you disconnect the output, then nothing is used, and it optimizes it to 0. It doesn't synthesize anything. And I'll bet you'll find that if you look at the use statistics in the compile box, I'll bet you'll find that the amount of hardware went to 0. That's probably what happened. Yeah, if there's no output, then it doesn't build it. Yeah, I've had a couple of times when I built Nios systems and compiled it, and it didn't use any space at all for the Nios blocks. There was zero size for the design. Because I forgot to connect the clock. Doesn't know it's a clock, this one. So, yeah, it's not a bad idea to cross-check by looking at the size of the design after the compilation and make sure that it's about the size you expect, because that'll tell you if something's been optimized away. Also, it is I had this pointed out to me again yesterday by the compiler, that it is a bad idea to ignore warnings. And I got caught by the misspell bug that car underscore strobe is not the same variable as car strobe. Of course. I used one in one place, one in the other place. And Quartus just happily synthesizes, makes up a variable with the name that is never defined, and then assigns it the value of 0. And it never changes. And you won't ever find that because it doesn't throw an error unless you check the warnings, in which case it will say created implicit net. If you see anything, if you see any warning that says created implicit net, you're doomed unless you fix it. If it's a 1-bit signal, you might get away with it. If it's a multiple bit signal, it will never work. So always check. There's a lot of errors you can ignore. You know, pin is not driven. Character or 32-bit constant was truncated to 5 bits to match the size of. Those are all stylistic things you can get away with, but an implicit net warning will kill you. You have to look for those. Or at least you have to look for them if you start getting results you don't understand. What I was doing was geeking it up, figuring out how to connect the LCD display to the Pancake microcontroller. And it didn't work because it wasn't actually the character strobe that I forgot to declare. It was the character. And so instead of passing a 9-bit number, it was passing a 1-bit number, and it was not showing anything on the display because everything was 1 or 0, which is an unprintable character. So do not ignore the warnings. Do not ignore critical warnings, unless you're sure you can. Any other questions about Lab 3 or 4?
If the drum is too big, you can actually hear the returning wave. Is that okay?
So you hear a thump and then it comes bump back again?
It depends on the speed of sound. But it's clear that you hear bump like coming back.
I think that's okay. Yeah. How big is your drum?
Now 28,000.
28,000 nodes? So that's like 100. No, it's 150 by 150 or something.
It's not square.
Ah.
It's 200 times 34 times 4.
Wow. That's huge. Oh, cool. All right. Yeah. What's the driving function like? Is your driving function fairly peaked, or do you have a nice smooth? So it's smooth. Because if it's peaked, then I expect to hear some dispersion on the grid. You start hearing kind of sounds in the background.
6, 7 notes. 3 plus and down.
In both directions. That should be good enough. Now I'd like to hear it. Anything else on Lab 3 or 4? All right, well, let's continue on with talking about Nios software. Mark's comment last lecture that there should have been an ampersand in front of the flag was completely true. I just left it off. So I'll start again with Alt IRQ, register which associates the timer 0 IRQ with a given interrupt service routine. Timer 0 IRQ is a constant value between 0 and 31 that comes out of the system.h file. And we want to cast a pointer to flag, as Mark said, and I blew him off. And then point the system to timer ISR. So that's a pointer. That's a pointer to function, right? And then there were two statements that opened the LCD, and then I believe where I left off was getting into the inevitable endless loop that every embedded program must have. And what we're going to do here is read the switches, display a node index on the LEDs, output the direct digital synthesis increment, and then print the frequency of the direct digital synthesis to the LCD. So that's all it's going to be in the loop. It just goes around and around reading switches. So our switch variable, and I could write this as IORD underscore Altera underscore Avalon underscore PIO underscore data in 0 underscore base, but instead I'm just going to write this as IORD for IO read. Again, in 0 underscore base is an address of the IO unit that comes from system.h, and it turns out that the offset of the data register, so the PIO parallel IO control block has an offset 0 corresponding to data. Offset 1 I think is direction. So we want an offset, we want to read the data from this parallel IO device, so we're going to set the offset to 0. Then we're going to do an IO, write to out1 underscore base. You write, for an IO port, you write to the same port that you read from, so the output data goes to offset 0, and we're going to output the flag, which is being updated in the interrupt service routine, so that the device which is connected to the out1 base, which is the green LEDs, red LEDs, will just indicate the binary equivalent of the flag variable, which goes from 0 to 8. Then we do an IO write out 0 base, offset 0, data equal to notes of index flag. So notes was an array of frequencies in hertz. And if you'll remember, I said that the frequency of the direct digital synthesis, the increment corresponding to a frequency we desired of f, is given by f times 2 to the 32 over the clock frequency for a 50 megahertz clock, and for a 32-bit direct digital synthesis register, this works out to f times 85.89934, but that's pretty darn close to 85.9. So what we're going to do here is to multiply by 859, because I didn't want to use floating point arithmetic, times the switch. So we're using the switch to offset the frequency, and we're going to divide this by 10, which then rounds this to 80, or it makes it equivalent to multiplying by 85.9. So the last thing we have to do then is the easy part, which is an fprint f. You remember we opened an IO unit. We opened a file called LCD underscore FD. LCD underscore FD. That's a file descriptor. In this case, it routes the stream, the character stream from the printf to the LCD. And then we have to specify the usual obscure C format string. And what we're going to specify is we want a character output, then we want a string, Then we want the characters frequency equals, then a space, and then a integer, then 2 spaces, and then a \n, which is a new line. Go to the next line. And that's plenty obscure. %C says take the next parameter, which is going to be the escape character that we defined last lecture. Take the escape character, throw it out through the file unit. Then take the string ESC underscore bottom left, which is a VT100 control string we defined last time. Output that string, then output the literal characters frequency equals space, then %D, which in this case is going to be notes of flag times switch. So it's going to be an integer corresponding to the frequency that was actually produced in hertz. And then we end the while, and then we end main. So the printf, the fprintf, acts as if there's an operating system there. It acts as if Unix is wrapped around this program, but it's really just a CLIB that's simulating the I/O functions, very limited I/O function simulation of Unix. For instance, it doesn't support a disk drive, I don't think. But this kind of structure makes it very easy to do an fprintf to the LCD for debugging. So you can always find out where in your program you are. You can put little messages up. The LCD is 2 lines of 16 characters. It's not huge, but that's quite a lot of space for debugging. It is not, however, very fast. The fprintf is a blocking function, and it takes about a millisecond per character to print this. So this string is going to take 1 plus however long this escape bottom left string was. I think it was about 4 characters. So that's 4, 5, 6, 7, 8, 9, 10, plus the conversion to int. So it's probably going to print between 10 and 12 characters, so it's going to take 10 or 15 milliseconds to execute this. It's not a very fast thing to do. Don't ever put an fprintf in an interrupt service routine. It will kill it. So we've sort of gone through the process of building a computer using SOPC Builder, then embedding the CPU into a hardware environment in Verilog. And then once it's embedded in the hardware environment, connected to the switches and the LEDs and the LCDs and so on, then we can write a program for it. And I suggest using the Altera Monitor program rather than the Nios IDE. But that's going to be the overall process that you're going to use in Lab 4 to produce the device which commands your parallel processor. There's going to be a NiosII, which is the master node for all of the iterators that you're going to build. Unless, of course, what you want to do is you want to have multiple Nios. You can define multiple Nios CPUs You just append them to the bus in SOPC Builder. You get a module out. You get a module out that includes the interface to all of the CPUs. One module gives you the interface to all of the CPUs. You connect the CPUs to whatever outside stuff you want, and then you write separate programs to execute on each different CPU. I don't know if you can use Altera Monitor program to program multiple CPUs or not. I've never tried it. You may have to go to the NiosII to do that, although I suspect there's a way around that. So it is possible to put, probably 4 or 5 or 6 Nios CPUs on the chip. But remember that if you execute off of SDRAM, there could be a memory choke point for multiple processors, unless you define the instruction cache big enough on each processor so that the first time through it hits memory, and then after that it executes out of cache. And then it could be very fast. You can specify the cache size in SOPC Builder of each CPU. Any questions about this? I know it's a little abstract because it's a whole 4 days away before you have to start this, but it's what other details do you want to know about the microcontroller? There's examples here. There's examples online. All this code's online in the, I think it's called, off the main page, I think it's called something like NiosII examples. The page is called NiosII examples. There's also a page that has assembler examples if you're really masochistic. Actually, MIPS assembler is fairly straightforward. It's just tedious. I don't see any reason to use it. There's also an operating system that runs on top of C for these microcontrollers. I can talk about that if you want, if you think you're going to use the micro C/OS operating system. It's really very nice. That, by the way, is pronounced generally mucus. Some things shouldn't be pronounced. But micro C/OS is a very nicely worked out, very simple operating system in some ways. The nicest thing about it is the entire source code is available in a book. And so you buy the book for whatever, 50 or 60, it's probably $250 now, I don't know. When I bought it, it was 50 or 60 bucks. And you read the book and you know how the operating system works. It's kind of a dry read, realistically. I mean, you got to really want to read it. I decided I was going to write an operating system once, so I read it. But it's clearly written. It's a very nicely written book. And once you read through that, then you completely know how a real-time operating system works. But if somebody wants to hear about micro C/OS, I will talk about it. Otherwise, I'm not going to. In fact, starting pretty soon, the topics for the individual labs are going to be done. The topics that are required to get through the next week are going to be done. And we can talk about more general stuff. And so what do you want to hear about? What do you want to do for final project? I'll talk about anything reasonable that I can write a lecture about. Some things I've done in the past is much more on DSP, parallel DSP. I can talk about soft radio. How would you build an AM radio on this architecture, or an FM radio? Head-related transfer functions and spatialization of sounds. Reconfigurable computing, whatever that means. Evolutionary computing. How would you set up the FPGA to modify itself on the fly? That could be fun. Or cellular automata. So whatever you want to hear about, I'll be happy to talk about, but I need to hear it. Otherwise, I'm just going to make it up. Probably by, this is October 5th or 6th or something like that. Probably by the first week in November, I won't be lecturing anymore. Probably by then we'll just go to the lab every morning and work on final projects for the whole month of November. That's one assignment for the last 5 weeks of classes. Build whatever you want. But you need to start thinking about that now. Alex? No homework in this class. I just assume that you're going to do it. Obviously, we'll be happy to talk about whatever you want to do and try and give you some suggestions. I'll be happy to talk about it. Darwin will be happy to talk about it. We'll kick ideas around. We'll do it any way you want. Be happy to talk more about final projects, what's been done in the past, for instance, what I think some interesting projects are. But you have to start thinking about it like now, because it's only 2 weeks away, more or less. I think we finish with this, with Lab 4 on October 28th. I think that's the Friday, right? Is that, yeah, October 28th. And then the next 5 weeks is solid. So by the middle of October, you need to have a good idea of what you're going to do for a project and be reading up on it. So that gives you, say, a week or 2 weeks to figure out what you're going to do. Start talking to your partners now. Start figuring out what you're going to do, because it's coming down the pipe at you. Heard one idea this morning from Cooper, who is not here. He's probably sitting in the lab, since that's where he was this morning. And he was in there. Oh, I hate. Well, he looked pretty good this morning. He didn't look like he'd been up all night, but you know, people can fake me out. If I did that, my teeth wouldn't fit in my mouth. So, what he was thinking about doing is interactive version of John Conway's Game of Life. You know Conway, John Conway, famous mathematician. He invented this cellular automaton. It's a 2D automaton. It is interesting because it is Turing complete. You can build a computer out of it if you want. And the rules are simple. Each cell has 8 nearest neighbors. 1, 2, 3, 4, 5, 6, 7, 8. If it has one nearest neighbor and it's alive, has binary 1, it dies from loneliness. If it has 2 nearest neighbors, it stays alive. If it has 3 nearest neighbors and it stays alive, or if it is not currently alive, it becomes alive. It goes from 0 to 1. And anything more than 3 neighbors and it dies of overcrowding. And it turns out that is a compute universal rule. So you can build anything. People have built the strangest machines in Conway's Game of Life. The interesting part of this, well, there's a couple of interesting parts. One is, how do you update this at video rate? How do you update, say, a 1280 by 1024 array of these things at video rate, which you could do on the big system we have on the DE2 115. I know that's doable. And the second is, how do you make it interactive so that you can get a pattern that might have 200 or 300 active cells off of the web and download it directly to your automaton calculator, so that you don't have to enter by hand some pattern with hundreds of active cells in it, which you never get right. So a web interactive game of John Conway's life simulator would be quite interesting. Another possibility, another automaton, cellular automaton, which I think is very cool, is Wireworld. Wireworld. Let me now write it so you can read it. Google up Wireworld, and you'll get a couple of, I don't know, some pet sites or something, and then but you'll get an automaton site. And Wireworld is a automaton, a cellular automaton that simulates current flow in wires well enough that you can build a computer with it. It's also compute universal. Very simple rule, extremely simple rules for Wireworld. And somebody has actually built a digital computer out of this and programmed it to compute prime numbers, and and you can watch this running in Java. So if you Google up Wireworld compute a Java applet, you'll be able to see the animation of this thing. It is really twisted. I don't know how you design that. Another possibility would be to do a dynamic simulation, a particle simulation. Let's say you made a simulator that could animate particles with collisions, so you can scatter one particle off of another. Then you should be able to simulate a classical gas. So you ought to be able to put a weight on top of this, and it would slide down until the pressure of the particles held it up. So you could do a particle simulator would be interesting. This is not a cellular automaton. It's a particle simulator. It would be a dynamic particle simulator where you either have collision or collisionless particles, depending on what you want to do, and simulate things like waterfalls, fireworks. So if you have a set of steps like this and you allow 10,000 particles to start here and fall under gravity, you get bouncing down here. It looks like a waterfall. If you have 10,000 particles that all start in a small ball and fire radially outward with a velocity which decreases exponentially in time, you get something that looks like a fireworks explosion in the sky. If you put these out of a tube and blast them up into the air with a small random component to the side, you get a fountain. So you can imagine building a more or less general particle simulator. If you could make it run in parallel fast enough to do an interesting number of particles, I'm guessing interesting in this case would be greater than 1,000 at animation rate. I think you probably have to do 10,000 at animation rate. Animation rate being faster than, say, 30 frames a second. You could do DSP-like things. You could do simulations of an orchestra. Simulate all of the instruments. Simulate the drums, you know how to do that. Use Karplus-Strong algorithm to simulate strings and maybe horns. Make a complete virtual orchestra. You could make a kick-ass special effects generator for a guitar. Because you have a huge amount of bandwidth, feed your electric guitar signal into the mic input, pump it through a big parallel processor and put it out the audio output, and just do brute force special effects, reverb, distortion, maybe a chorus effect. You could do all kinds of stuff with the bandwidth you've got available on here. Space Invaders. I think you could do Space Invaders easily because, after all, Space Invaders originally ran on an 8-bit microcontroller. And so I think you could do full 3D Space Invaders on here. Oh, another possibility would be 3D graphics. Build one of these big microcontrollers, program it up with a graphics algorithm. Anybody take computer graphics? There you go. You don't have to do a project. You already did one last year. By the way, the project Darwin did last year was a combination of computer graphics and audio analysis to try and do some interesting visualizations of music, more interesting than, say, Windows Media Player, extracting sort of geometric primitives from real-time music playing. What do you think? Any ideas? Any hallucinations? Strange things you always wanted to do if you had infinite computing? Well, infinite's a relative term, of course. I like automata. I like differential equations. There's another automata. There's another cellular automata which simulates gas. It simulates an ideal gas. I'll have to look it up. I can't remember the name of the rule. I programmed it up once in MATLAB, though, and it allows you to do things like wind swirling around a barrier, classical fluid flow around arbitrary objects. Nothing? No ideas? Get thinking, folks. Talk to us in the lab. Talk to Darwin and I in the lab. Start figuring out what you're going to do, because the end of the semester is moving towards us at a frightening rate. And so about 3 weeks from now, you need to start final project, which means no more than 2 weeks from now you have to know what you're going to do. What if you could do a driving simulator? Get all the car dynamics running on one processor, and indicator controls, dashboard running on another processor. Could be fun. Anything you want to hear about? You'll know. It'll be clear if you want me to do a lecture. It'll be clear after you figure out what you want to do for a final project. If you want to hear about some specific thing, as I said. Otherwise, I'll talk about some fairly general stuff. I'll probably start talking about narrow floating point next time if I don't hear something else from one of you. Start talking about ways of doing 9-bit and 18-bit floating points so you don't have to go full IEEE. Probably talk more about DSP. Darwin? Yeah. I have a duck hunt gun sitting in my office. Somebody from 4760 left. And that would be interesting to do with VGA monitor. Yeah. Somebody last year did this interesting application where they stared at the at the user with a camera, and the user had different colored tape wrapped around two fingers, and by hiding one of the other colors of tape, you could produce drawing commands, so you could trace your finger in the air and draw on the screen. And they got good enough at it that they could draw good pictures, and you fold that finger under, and then you can move your hand without drawing. You put it back out again and you draw some more. So it was just an air interface to a drawing program. And some color control depending on the other. There was a menu you could choose with different combinations of the two colors on your fingertips, depending on what you were hiding from the monitor. Another group last year did 3D extraction. So they had two cameras they hooked up to one computer. They looked at the binocular disparity and attempted to get the depth in real time from the images. It was, I would say, moderately successful. Another group did a really cool project, which was a real-time cartoon extractor. So it did full real-time edge extraction, took the image, reduced the color palette to a few colors, propagated the colors through the internal regions, so you got very flat colored looking objects or barely shaded objects that were all outlined with what looked like pencil lines. And so you got a very cartoony looking image out of it. One guy did a cellular automaton, a 640 by 480 automaton that ran at full 60 hertz and could be a model for other automata. It was the falling sand game, which you probably have seen on as a flash animation or as a game on a PC, except his was much faster. Think about stuff that requires lots of computation. There's also infrastructure kinds of projects that would be interesting to do. Take the Pancake microcontroller and interface it to the Ethernet port. Write a TCP/IP stack for it. It's a lot of work. But you could probably do a UDP interface to the Ethernet port. Might be interesting to try and do some compression stuff. However, if you try to do compression stuff, I would suggest against trying to go to some standard. Like, don't try and take images all the way to JPEG, because that's a real the bit description is awesomely complicated. You surely do not want to try and take a video all the way to MP4. I think that's years of programming effort. But there are some compression things that could be done. Probably some music compression could be done. Start thinking. Any other suggestions, Darwin? Anything come to mind?
I was just wondering how well the MP3 project went last year. I can't remember.
I don't think they got very far on it. I think they got some stuff done, but again, going to MP3 is a difficult thing because there's person centuries of optimization in it to make it a commercially viable bit stream. And it's just very hard to get it right. But you could do some compression fairly easily if you don't take it all the way to MP3. Anything else? Any other ideas? Wacky things you've seen on the internet you wish you could do? Computing-wise, that is. All right. Start thinking. Come in next time with some ideas for final projects. It's getting close.